Welcome to Tomorrow Unveiled, where we dissect the future one breakthrough at a time. This week, we're doing something a little different. We're zeroing in on a very specific 7-day period, November 14th through the 21st, 2025.
And it might sound random, but the analysis from our dedicated research team shows this week was, well, it was pivotal.
It really was. This wasn't just another week of, product announcements. This was the moment that the wearable, the device on your wrist or your face stopped just watching you.
And started actively integrating with you. That whole passive era, what we used to call the quantified self.
Right, where it just counted your steps, maybe tracked your sleep, and gave you a chart.
That's really coming to an end. The theme for this deep dive on Tomorrow Unveiled is strapped in. And that's because it's about this new bidirectional relationship.
Bidirectional, meaning it's not just taking data from you, it's giving it back in a much more meaningful way.
Exactly. The wearable isn't just a tracker anymore. It's closing the loop. It's becoming, in a very real sense, an extension of your nervous system, your senses, your ability to control things.
And what's so interesting is that this isn't just happening in research labs. This shift is being validated at the highest levels. I mean, the intelligence the team compiled points to these two huge signals from the FDA this week.
Yeah, those are critical. The first one, for continuous glucose monitoring, the Dexcom system. It got clearance to be part of an AI-powered insulin optimization system.
So it's not just telling you your blood sugar, it's actively intervening. It's making therapeutic decisions.
Precisely. And the second one was just monumental. The clinical clearance for Paradromix fully implantable brain-computer interface, or BCI.
That feels like science fiction.
It does, but these clearances, they're more than just product news. They're signals of regulatory maturation. Basically say, okay, this technology is stable enough, it's accurate enough, it's safe enough to move out of the lab.
And into actual medical use, capable of changing lives.
And that changes everything. How we design them, how we secure them, how we govern them. It's a whole new ballgame.
So for you listening, our mission today on Tomorrow Unveiled is to break down how this integration is happening. We've structured it around 3 key points of convergence.
First, we'll look at how tech is getting way better at decoding human intent. That's the input layer.
Then we'll get into this incredible breakthrough in digitizing the sense of touch. That's the output layer.
And finally, we'll look at the commercial fight for real estate on your body. The glasses, the rings, that's the battleground for who wins the consumer.
All right, let's dig in. The input problem. If a machine is going to be part of you, it has to understand what you want it to do, right?
And with extremely high fidelity. For years, there's been this one massive technical hurdle that just sabotaged everything. Motion artifacts.
The noise. It's the reason your heart rate monitor suddenly spikes to 200 when you start running, even though you feel fine.
Exactly that. It's the static that corrupts the signal. And for neural interfaces, which are trying to pick up these impossibly tiny electrical signals from your nerves, signals in the microvolt range.
So incredibly faint signals.
Right. And the noise from simple physical movement, a sensor rubbing against your skin, it's like a physical jackhammer next to a whisper. The noise completely overwhelms the actual biological signal.
By a factor of hundreds, according to the research.
Sometimes, yeah.
Yeah.
Which makes precise, real-time control basically impossible, unless you're sitting perfectly still in a lab.
Which is, not how the real world works. So this seems like an unsolvable physics problem. But the research team we analyzed found this breakthrough from UC San Diego that appears to have cracked it.
It's a really elegant, multi-layered solution. It combines material science with some very clever AI.
So how did they filter out the jackhammer?
Well, first, they rethought the physical interface.
Mm-hmm.
They didn't use a stiff, rigid armband that would slide around.
Okay, that makes sense. Less sliding means less friction, less noise at the source.
Exactly. They developed a soft electronic forearm patch. It's made of these highly conformable, stretchable electronics. It's designed to move with your skin, not against it.
Almost like a high-tech temporary tattoo.
That's a great analogy. By moving in sync with the tissue, the relative motion, and therefore the noise, is hugely reduced. But you're right, that's not enough on its own. Any violent movement will still create some noise.
And this is where the intelligence comes in, the AI.
This is the critical part. The patch has a custom deep learning algorithm, a neural network that lives directly on the chip.
So it's edge computing. The processing is happening right there, on your arm.
In real time.
Mm-hmm.
This AI was trained on just massive amounts of data. It saw the biological signals they wanted to capture, but it was also trained on every kind of disruptive motion you can imagine.
Like running, jumping.
Running, jumping, shaking, even data that simulated being in a vibrating vehicle or in turbulent ocean waves.
So the AI essentially learns what noise looks like. It learns the signature of the interference.
Precisely. It can then mathematically subtract that noise signature from the overall signal in real time, leaving behind only the clean biological command.
A digital noise-canceling headphone for your nerves.
That's it. It differentiates instantly between the chaos of mechanical noise and the subtle, deliberate electrical signal of you wanting to make a gesture. And because it's on the device, the latency is almost non-existent.
So what here is that this takes neural control out of the lab and into the messy real world.
It completely changes the game. The source is confirmed. This allows for reliable control of, say, robotics, even in these chaotic high-motion environments.
What are some of the applications they're looking at?
Well, think about a diver operating a remote vehicle underwater. They're fighting currents, there's turbulence.
It's a very noisy environment, electrically and physically.
Exactly. Before, gesture control would be useless. Now they could potentially control a complex machine just by flexing their forearm muscles, even while navigating. The research team also flagged industrial workers, in factories with heavy, vibrating machinery who need hands-free control. This makes that interaction safer and more reliable.
So that's the absolute cutting edge. But this whole philosophy, this strapped-in idea, is also hitting the consumer market. And Meta is right at the forefront with their neural band.
Meta's goal is a little different. It's about social acceptability and making augmented reality seamless to control. They're using a technique called surface electromyography, or SEMG.
So instead of trying to listen to the brain directly, they're listening to the signals the brain sends down the arm to the fingers.
That's it. They're tapping into the existing wiring. This is their big solution to what some people call the gorilla arm problem in AR.
Right, the fatigue and just the social awkwardness of having to hold your arm up and poke at virtual menus in the air.
Nobody wants to do that on the bus. The neural band is designed to detect what are called microgestures.
Okay, what's a microgesture?
It's the electrical impulse traveling down your nerves to your fingers before your fingers even visibly move. The intention to move, captured as a signal.
Wow. So I could be sitting with my hands resting in my lap and I could just think about tapping my index finger.
And the band would pick up that neural command.
So I could scroll through a menu, click a notification, answer a call, all without visibly moving my hands.
That's the vision. It makes the control system functionally invisible to everyone around you. It's discreet, it's hands-free.
Which feels like an absolute prerequisite if AR glasses are ever going to be something people wear all day, every day.
It has to be. The interface can't be clunky or awkward. This SEMG approach turns your own hand into this universal, always-on remote control for your digital life.
Okay, so we've covered conquering noise with on-device AI, and we have this discrete commercial input for AR. But let's talk about the really high-stakes frontier, the invasive stuff. The big regulatory news of the week was the FDA approval for Paradromix and its Connexus BCI.
This was a huge milestone. It signals that this technology is maturing beyond just speculation. This is a fully implantable device.
And it received approval for human trials specifically aimed at restoring speech.
For patients with severe paralysis, yes. People who have lost the ability to speak.
What makes the Connexus system such a breakthrough? The research team highlighted a really specific technical detail, the data rate. Over 200 bits per second. Why is that number so important?
That number, that bandwidth, is the difference between being able to type out a few words a minute and having a fluid, natural conversation.
Okay, so older BCIs were more like very slow, single-finger typing.
Exactly. Extremely laborious. But 200 bits per second? That's fast enough to translate neural activity directly into conversational speech, in real time. It opens the door to expressing complex thoughts, nuances, emotions, not just picking from preset phrases.
Can you give us some context on just how difficult that is to achieve?
It's immensely difficult. I mean,
Okay.
the Connexus system uses this dense array of microelectrodes, over 400 of them, that actually penetrate the brain's motor cortex to capture these signals with high fidelity.
Wow.
And the complexity isn't just in the hardware's ability to read all that data, it's in the decoding algorithms. You have software that has to analyze hundreds of channels of brain activity at once and translate those chaotic firing patterns into coherent language. And it has to do it in milliseconds.
So the FDA approval means they're confident in both the physical implant and the AI that translates the thoughts.
It's a green light for the whole system. This is the technology for high bandwidth conversational brain-computer integration is ready for the clinic.
Incredible. So just to recap the input side of things for this week, we've solved motion noise, we've commercialized discrete gesture control for AR, and we've had a clinical validation for BCI that can literally give people their voice back.
The ability for our technology to understand human intent has has really crossed a major threshold.
Okay, so if that's the input side of the equation, let's look at the other side of the loop, output. How does the machine talk back to us?
And this has always been the weak link. I mean, what good is it if the wearables can understand your most subtle intention, but it can only communicate back with the sophistication of, like, a pager from the 90s?
You're talking about the haptic gap. We have these incredible high-resolution screens for our eyes, hi-fi audio for our ears, but for our sense of touch, it's just a
The
buzz.
binary buzz, exactly. It's on or it's off. Most wearables use the tiny motor that just vibrates. It can tell you one thing. Hey, something happened. An alert.
But it can't convey any of the richness of the real world. Texture, friction, pressure, warmth.
None of it. It's like having a display with only one giant gray pixel. It's incredibly low-resolution information.
But the research our team analyzed points to a breakthrough from Northwestern University that seems to, well, fundamentally change that. The Voxelite system.
The Voxelite is, and this isn't an exaggeration, it's like the jump from standard definition to 4K television, but for the sense of touch.
And it's a bandage-like film, something you wear on your fingertip.
Exactly. It's flexible, it's low profile, and it doesn't use little motors. It achieves this incredible resolution by manipulating the physics of friction and pressure right at the surface of your skin.
Let's get into the mechanics of that. The sources mention two key ideas, these miniature fluidic nodes and something called electroadhesion.
Okay, so think of the fluidic nodes as taxels, tactile pixels. They're arranged in this grid, and the spacing is less than a millimeter apart.
Which importantly matches the two-point discrimination threshold of the human fingertip.
You got it. It means the grid is dense enough that your brain can perceive distinct points of contact. So the spatial resolution is there. It's high def.
But what about the feeling? How does electroadhesion create the sensation of, say, sandpaper versus silk?
Electroadhesion is the real magic here. The device applies a tiny electrostatic force to your skin, which allows it to electronically control the amount of friction. By rapidly changing the voltage, it can make the surface feel sticky or slippery.
Okay, so it's modulating friction.
Right, and at the same time, those little fluidic nodes can slightly indent or depress the skin, which simulates pressure and the bumps of a texture. When you combine that controlled friction with controlled pressure, you can convincingly mimic the sensation of sliding your finger across almost any surface.
And the speed it can do this at is also a huge factor, right? The research says it can actuate up to 800 times a second, 800 hertz.
That speed is absolutely vital for making it believable. Our touch receptors, especially the ones that detect fine textures and vibrations, operate across a huge frequency range. If your device can only buzz at, say, 100 hertz, you're missing most of the information.
It would be like trying to listen to an orchestra through a subwoofer. You only get the bass.
Perfect analogy. By operating across the full frequency range, up to 800 hertz, the Voxelite can stimulate all the different receptors in your fingertip. It essentially tricks your brain into perceiving a real texture that isn't there. It's the full digitization of touch.
The applications for this feel immense. The obvious one is e-commerce, being able to feel the woof of a shirt before you buy it online.
That could be a complete game changer for online retail. Think about feeling the texture of a leather couch or the grain of a wood table. But honestly, the professional applications are even more profound.
You're thinking about things like medical training.
Absolutely. Surgical training in VR. For a surgeon, the feel of tissue is critical information. Distinguishing a firm, unhealthy tumor from soft, healthy tissue is a life-saving skill.
And you can't learn that just from looking at a screen.
You can't. But with high-resolution haptics, a surgeon training in a simulation could actually feel that difference. They could build the muscle memory and the tactile skill needed for complex operations without ever putting a real patient at risk.
And the fact that this is a thin, lightweight bandage, that feels key to adoption. It's an imperceptible wearable.
It overcomes the biggest challenge for haptics, which has always been comfort and bulk. If a device is heavy or gets in the way, people just won't wear it. The Voxelite's form factor, weighing less than a gram, means it can be worn all day. It's not just for specialized training, it can be part of your daily interface with the world.
So the pieces are falling into place. We have high-fidelity input through neural control, and now high-fidelity output through human resolution haptics. The technical foundation is there.
And with those technical walls coming down, the commercial world is now in this fierce battle over the form factor. Where on your body will this new interface live? And the fight is really centered on two places, the face and the finger.
Let's start with the face and smart glasses. According to the sources, Meta's strategy this week wasn't about one killer product. It was more of a segmented assault on the market.
Yeah, they seem to have realized that one size fits all just doesn't work for something you wear on your face. They're targeting the enthusiast, the mainstream user, and the niche athlete all at the same time.
So first up is the high-end model, the Ray-Ban Meta display.
Right. This is the one for the true AR believers. It has the LCS display liquid crystal on silicon, which projects actual digital images onto the lens. And crucially, it's designed to be paired with the neural wristband we just talked about.
So that's the full suite, the advanced visual output and the advanced neural input working together.
That's their top-tier, fully integrated vision of the future.
Yeah.
But it's also expensive and technically complex, which limits its appeal right now.
Which brings us to their second device, the mass market play, the Ray-Ban Meta Gen 2. And the fascinating thing here is what they left out.
They took out the display, which sounds counterintuitive for smart glasses, but it's actually a brilliant move for mass adoption.
How so?
By removing the most expensive and power-hungry component, the display, they can hit a much more accessible price point. And they focus the device on things that have an immediate, obvious utility. High-quality AI audio, 3K video capture, and a really impressive 8-hour battery life.
So it's positioned less as an AR device and more as an ambient AI assistant.
Exactly. It's your headphones, your action camera, and your AI helper, all in one, powered by that on-device edge AI. It's a much easier sell to the average person.
And then there's the third prong of their attack, the Oakley Vanguard.
This is their niche play, going straight after the serious athlete market, directly challenging companies like Garmin. It's ruggedized, it's packed with fitness sensors, and it has deep integration with platforms like Strava.
So it's a performance tracker and an AI coach built into a form factor that athletes are already comfortable with.
It's a classic market segmentation strategy. Cover all the bases to dominate a new category.
But Meta's closed ecosystem, their Apple-like approach, is facing a big counterattack, right? From the open ecosystem led by Google.
This is the same battle we saw with smartphones. Meta is building the hardware and the software, a tightly controlled experience. Google, on the other hand, is just providing the operating system, Android XR.
And they're partnering with everyone, fashion brands, tech companies.
Right. Samsung, Gentle Monster, Warby Parker. The analysis shows that Google believes the biggest barrier to smart glasses is style and comfort. So they're letting the fashion experts handle the frames, the look, the feel.
While Google controls the software brain inside.
It's a bet that variety and choice will win out over a single integrated vision. Let the user pick the style they actually want to wear.
But that open approach creates its own problem, doesn't it? Fragmentation.
It's the classic weakness. If every pair of glasses has a different screen or different sensors, it's a nightmare for developers. That's where this other initiative, AugmentOS, comes in.
So AugmentOS is trying to be a universal translator for AR.
In a way, yeah. It's an attempt to be the neutral, cross-compatible Android of AR. A standard layer that developers can build on top of, knowing their app will work on glasses from Samsung or Warby Parker or whoever comes next.
Okay, let's shift from the face to the finger, the smart ring wars. This form factor seems to be quietly gaining a lot of ground.
It is, and it's primarily because it's the most comfortable and least intrusive way to do continuous, 24/7 health tracking, especially for sleep. You just forget it's there.
And the finger is a great spot for getting good data, right?
It's excellent.
Yeah.
You get a strong, stable signal for things like heart rate variability and skin temperature, which are fantastic indicators of your stress levels, your recovery, your sleep quality.
Yeah.
But it's a really competitive market.
And the research team noted that Aura, the market leader, has been very aggressive with its patents.
Extremely, which has put a lot of legal pressure on competitors like Ultrahuman.
But the leak about the upcoming Ultrahuman Ring Pro shows a really clever response to that pressure.
It's a fantastic strategic pivot. Instead of trying to fight a patent war over sensor placement, they're changing the ring's core utility. The big news is the expected inclusion of NFC.
Contactless payments.
Right. And that single feature transforms the device. It's no longer just a wellness gadget you might forget to charge. It's your wallet.
Which makes it way more essential to your daily life. It increases the stickiness.
Exponentially. If you use your ring to pay for your coffee every morning or to get on the subway, you are far less likely to ever take it off. It makes the health tracking a great bonus feature on top of an essential productivity tool.
And we're also seeing the smart ring gain some serious medical credibility, like with the Progeny and Aura partnership.
This is a huge sign of the form factor's maturation. Progeny is a major fertility benefits provider for large companies.
So they're using Aura with the data to help track reproductive health and fertility cycles.
Yes, and that moves the ring out of the consumer wellness space and into the world of corporate benefits and clinical oversight. When your doctor and your insurance company are integrating this data, it means the technology has reached a level of accuracy and reliability that they trust for making medical decisions.
We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the future of haptics and neural control. If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
Before we move on to the foundational tech that makes all this possible, we really have to address the elephant in the room, the friction point that comes with this level of deep integration.
Privacy and security.
They become paramount. As these devices get closer to being extensions of our own minds and bodies, the risks just multiply.
We're already seeing the social friction, right? The return of the glass hole phenomenon, where people are just uncomfortable with the idea of being filmed constantly.
It's a very real social conflict.
Yeah.
And the research team flagged the emergence of what they're calling the privacy light war.
What's that?
Well, smart glasses are legally required to have an indicator light that shows when they're recording. But there are already third-party products being sold online designed to cover up or mask that light.
So there's a direct battle between a user's desire for discretion and the public's right to know they're being recorded.
Exactly. And the risk is evolving beyond just passive recording. The real concern is active, AI-powered surveillance.
When these glasses have powerful language models running on them.
They could be capable of real-time facial recognition, emotion detection, behavioral analysis. You're not just being recorded anymore. You could be being identified, analyzed, and categorized in real time by someone's AI.
Which raises profound questions about privacy in public spaces. How do you opt out of that?
You can't, really. And then there's the security risk, which moves from being about data to being about physical harm.
This is the most critical shift. We're not just worried about someone stealing your credit card number anymore.
No. When a wearable moves from just monitoring you to actively intervening, like an automated insulin pump or a BCI controlling a prosthetic limb, a security flaw becomes potentially fatal.
A hacker could, in theory, deliver a dangerous insulin dose or cause an industrial exoskeleton to malfunction.
A denial of service attack isn't an inconvenience. It can be catastrophic. The security for these devices has to be medical grade, life critical. The stakes are just that much higher now.
Okay, so with those risks in mind, let's talk about the foundational tech that's enabling all of this. None of these breakthroughs are possible in a vacuum?
Not at all. They all depend on these fundamental shifts in really three areas: power, materials, and intelligence. You have to solve the constraints of the human body.
Let's start with intelligence. We've mentioned edge computing a few times, but let's really break down why processing data on the device itself is so non-negotiable for wearables.
It comes down to power, latency, and privacy. If you tried to stream the raw data from, say, a high-resolution EEG or that 800 hertz haptic sensor to the cloud,
Your battery would be dead in minutes.
minutes. Plus, the round-trip time, the latency of sending data to a server and getting a response back is just too slow. For real-time neural control or haptic feedback to feel natural, you need a delay of less than 10 milliseconds. The cloud can't do that reliably.
So edge computing uses these specialized, tiny, power-efficient processors right on the device.
Exactly. Things like neural processing units, or NPUs.
Yeah.
The research highlighted Google's Coral NPU platform as a key enabler here. It's designed to run these huge, complex machine learning models while sipping power, just a few milliwatts.
And that's what allows a device to be always on, always listening and analyzing without needing a charge every hour.
And it moves the device beyond just simple alerts. The real future here is using these NPUs to run what are being called foundation models of behavioral data.
So AI models train on vast amounts of long-term human activity data.
Billions of hours of it, sleep cycles, activity patterns, physiological baselines. By crunching all that data locally, on you, The AI can start to detect very subtle long-term shifts in your patterns.
And move from being reactive to being predictive.
That's the holy grail. It's not about telling you your heart rate is high. It's about predicting, based on weeks of data, that you might be at risk for a cardiac event, or a severe sleep apnea episode, or the onset of an illness days before you feel any symptoms. It becomes a predictive health partner.
Okay, so that's the intelligence layer. The second foundation is material science. You can't have a second skin wearable made of rigid plastic and bulky batteries.
It just doesn't work. The whole field is pushing for electronics that can stretch, twist, and bend like fabric without breaking. The breakthroughs are coming from conductive plastics and, amazingly, stretchable, fabric-based batteries.
Fabric-based batteries, how does that even work? You have to maintain power while the thing is being twisted and even washed.
It's an incredible engineering challenge. The latest developments involve weaving these ultra-thin, flexible electrodes directly into a conductive textile. The sources confirm these fabric batteries can be bent and twisted hundreds of thousands of times with almost no loss in capacity.
And that's what enables true smart clothing, where the power source is just part of your shirt.
It eliminates the need for a hard, bulky battery pack, which is the key to making things like that UCSD patch or the Voxelite bandage, something people will actually wear.
And on the industrial side, we're seeing this integration take the form of physical augmentation, the Hyundai Exible shoulder.
This is a really important shift for robotics. The Exible shoulder is what's called a passive exoskeleton. It doesn't have big motors or batteries.
So how does it help?
It uses a clever system of mechanical springs and linkages to offload the strain on a worker's muscles during repetitive overhead tasks, like on an assembly line. It reduces the documented muscle load by anywhere from 30 to 60%.
So the worker is literally strapped in to a device that enhances their own physical strength, reducing fatigue and preventing injuries?
It's about augmenting human capability, not replacing it. It's a huge application for an aging workforce.
So finally, let's bring this all back to the medical world. The consistent theme from the research is this aggressive shift from passive data collection to active therapeutic intervention.
The demand from clinicians for continuous, high-quality data from outside the clinic is just enormous. And one of the biggest holy grails has always been non-invasive, continuous blood pressure monitoring.
Right, because the traditional cuff just gives you one snapshot in time, and the process itself can raise your blood pressure.
It's called white coat syndrome.
Yeah.
But this project from research teams at UT Austin and NCSU is trying to solve this with a smartwatch.
How are they doing it?
They're using specialized radio frequency, or RF, waves. The watch emits a low-power signal that interacts with the arteries in your wrist, and by analyzing the signal that bounces back, their algorithms can continuously estimate your blood pressure with clinical-grade accuracy.
Which would be a massive deal for managing hypertension.
A complete game changer. And we're seeing this trend of moving clinical-grade tools into the home with companies like Beacon Biosignals.
They raised a lot of money this week.
They did, and it shows the market demand. Their waveband device is basically an FDA-cleared, clinical-grade EEG monitor that patients wear at home.
So instead of one night in a sleep lab, you get weeks of neurological data from a person's natural environment.
Right. And that allows them to identify these very subtle neurobiomarkers for complex conditions like early-stage Alzheimer's, Parkinson's, or severe sleep disorders. It validates this whole idea of the wearable as a serious diagnostic medical device.
So this week, November 14th through the 21st, 2025, it really feels like it's solidified an inflection point for this entire industry. As we've explored here on Tomorrow Unveiled, it's all about this push toward deep integration.
It really is. We've seen this convergence happening across three critical pillars. First, you have the intent layer, our ability to decode what a person wants to do using neural and EMG control, and finally, solving that problem of motion noise.
Second, we have the sensory layer. That profound breakthrough in human resolution haptics, giving the machine a way to communicate back to us through touch with a fidelity that we've never had before.
And third, there's the contextual layer. It's the power of edge AI, the on-device intelligence that can understand your long-term patterns and transform the wearable from a dumb gadget into a proactive, predictive partner.
The conclusion from all this seems pretty clear. The era of the passive wearable just counting your steps is over. We're moving quickly toward a future where these devices just dissolve into our body's own feedback systems.
And the ultimate measure of success for any of these will be when you, the user, completely forget you're even wearing it.
If you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners.
But this deep integration It really forces us to confront that central conflict we talked about, the governance of your own biological data, maybe even your own preconscious thought. The technology is clearly ready for this merger between human and machine. The real question for you to think about is who gets to set the rules.
Who governs the data when that line between your biology and the machine really starts to blur?
As we all become truly strapped in, how do we make sure these systems, the systems that can decode not just our actions, but maybe even our intentions before we act, are secure and governed in a way that protects us?
That is a critical question to consider as you navigate the future. Thank you for joining us on Tomorrow, Dale. We'll see you next week.